Before watching this video, hopefully you've watched the video about what is rate of change, because that introduces you to average rate of change and instantaneous rate of change, and provides the basis for this video. This video is more about how to calculate the average rate of change. If you look here, it's sort of summarized here. Rate of change for a linear relationship is basically just the slope of the line, right? y2 minus y1 over x2 minus x1. That should make sense based on that last video. And even for a non-linear relationship, for any sort of curve function that's not straight, basically the average rate of change is still just the slope between any 2 points on the graph. And the way we can find that is by applying this formula here, f at x2 minus f at x1 over x2 minus x1. And remember, really, f at x2 just means y2, right? And f at x1 is basically y1. It's just the y value at x1. So essentially, these two equations are the same thing, right? The one for a line and the one here, it's the same thing. So this is sort of a grade 9 formula here that applies. So how do we actually calculate the rate of change? How does it look in a problem? First problem here. So we have a graph of population growing. It looks like an exponential graph, which population often follows. So the graph says since 2006, that's when it goes between, find the average rate of change in the population between 2007 and 2009. So if we look here, first of all, where are 2007 and 2009? Well, it says actually that this graph starts at 2006. So I believe that's 2006 right there. That would make this 2007, 2008, and 2009. So it's basically asking us what the average rate of change of the population is between those 2007 and 2009. So if you think about it like that, it's basically what's the rate of change between 2007, which is at 100 people, it seems to be, and 2009 up here, which seems to be 400 people, right? And remember, we represent the average rate of change as the slope of the line between those 2 points, right? So basically the question is asking us, what is the slope of that blue dotted line there? And we can do that by applying our average rate of change formula. So we know, if we call this, by the way, if we call this our point 1 and our point 2, usually makes sense to go in order. We actually have to go in order of x. So the first one is 1, the second one is 2. So the average rate of change, ARC in other words, is going to be our f at x2, right? So our f in 2009, or sorry, our population in 2009 is going to be 400, right? And then we're going to subtract from that what the function is equal to at point 1 in 2007, which is 100. And then we're going to divide by basically the difference between those 2 years. And because the graph has 1, 2, 3, the years are 2007, 2008, 2009, it doesn't really matter which one we use, which one x2 and x1 are. I'm just going to use what's on the graph. So 3 minus 1, right? Either way, the difference is going to be 2 years. So if we plug this into our calculator, we can find that basically it's going to be 300 over 2, which is 150, right? That's going to be our average rate of change. Now we should include units as well. This part of the graph, or sorry, this part of the equation, the top part, that was our population, right? How our population changed. And the bottom part was our time, or our years. So when we divide these two things, the unit that we're going to end up with is obviously population per year, or people per year. People per year. So this value is positive, and it makes sense. The population, based on the graph, seems to be increasing. So every year, the population is gaining 150 people on average between 2007 and 2009. One more thing before we move on to the next question. When we're just reading the values off the graph like this, remember this is just an approximation. This graph looked pretty clear that it was at 100 and 400, but it's not always going to be that clear. So sometimes you might need to sort of interpolate between values to figure out what the, or to approximate what the value is. Now we have a question about the population, another population question, of bacteria after an antibacterial spray is applied to that bacteria. So we're given a table this time instead of a graph, and it's asking us, what's the average rate of change in the number of bacteria in the first 1.5 minutes, right? So the first 1.5 minutes, that's basically going to be between 0 and 1.5. How does the population change between 0 and 1.5? And we can basically apply the exact same idea that we did before. If we think of our time as our independent variable, like our x, oops, I'll do that in pen, as our x, and our population as our y value, it becomes very obvious. We'll call this the starting point, our 1, and this will be our ending point, our 2. So basically, how does the population change between those two, right? So our average rate of change is going to equal y2 minus y1. So it's just going to be 737 minus 800 over our difference in time, right? So our y2 or our x2, sorry, is going to be 1.5 minus 0. So once again, just to highlight, it's the change from here to here, right, minus the change from here to here. And if we do that calculation, we end up with negative 42. And again, looking at our units, our y part was bacteria or population of bacteria, so we'll just put bacteria. And our x, our time, was in minutes, so bacteria per minute. Does it make sense that it's a negative value? Well, look at the table and look at the context of the question. It's a bacterial spray that's applied to try to kill the bacteria, basically. So it does make sense that it's negative, because essentially what that means is that the bacteria is dying at a rate of 42 bacteria per minute, right? There are 42 less bacteria per minute in that first 1.5 minutes on average. Okay, so let's go on to the next question. What's the rate of change in the last 1.5 minutes? So here we're looking, basically the last 1.5 minutes will be, if the last time we have is 4, it's going to be from 2.5 to 4, right? That's 1.5 minutes. And the x values we're looking at there are from that 5:15, this will be our starting point this time, and this will be our finishing point this time, right? So our average rate of change is going to be the difference in the y values, so 0 minus 5:15, over the difference in our x values, which is 4 minus 2.5. And if we do this calculation, as the answer says right there, our answer should be about negative 343. I'll just round that and put a about sign there. So about negative 343 bacteria per minute. Okay? So what does that mean? That means in the last minute and a half, the bacteria is dying at a rate of 343 bacteria per minute. So notice how 42 bacteria were dying per minute at the beginning, and 343 were dying at the end per minute. So the rate that the bacteria are dying has increased. So next we have a bit of a physics problem. The height of a football is modeled by that quadratic equation, right? That one right there, where h is the height in meters and t is the time in seconds. So when it's asking us, what's the average rate of change in the first 2 seconds? Really what that's asking us is, what's the average rate of change, right? So we're looking for the average rate of change between 0 and 2 seconds, right? Inclusive. What's the difference between 0 and 2 seconds? So in order to do this, if we think about our equation, we go back up here actually to the previous page. You can think about it this way. We're looking for, right, the y2 minus y1, the function at our second point minus the function at the first point over the difference in our x values, right? So to do that, we need to know what the value of the function is at 0 and at 2, right? So if you plug in our value at 0, you could do that yourself. You'll see that it should just come out to 1. And the function at 2, if you plug in a 2 into our equation, it should come out to 21, I believe. Okay? So we now know what the function is at 0 and at 2. And if we call this sort of our first point here, our starting point, and we call this our ending point here, our average rate of change, we know it's just going to be y2 minus y1 over x2 minus x1, right? So our y2 minus y1 is going to be 21 minus 1 over our x2 minus x1, 2 minus 0, which gives us 10. What are the units for this question? Well, if you think about the height is our y value, right? So the height is actually in meters. So this is actually 1 meters high, and this is 21 meters high. And the x value is in seconds. So when we do this, these are going to be in meters, and these are going to be in seconds. So the answer is actually 10 meters per second. Okay, let's go on to the next one. What's the average rate of change between 2 and 4 seconds? Basically, that's what that means, right? So in order to do this, we need to know what f at 2 is, and we've luckily already calculated that as 21 meters. And then we also need to know what f at 4 is. Oh, I've been making a mistake here. I've been calling the function f. The function should be called h, right? So this should actually all be h's. So feel free to correct that. That's my bad. Anyways, h at 4, if we do that calculation, we plug that in, we should get that h at 4 is equal to 1 meter, just by plugging it into the equation. So when we're solving this one, it's the same idea, y2 minus y1 over x2 minus x1. So our average rate of change is just going to be, it's going to be 1 minus 21, right? If this is our second value and this is our first value, 1 minus 21 over 4 minus 2, that gives us an average rate of change of negative 10 meters per second. What could that possibly mean? And why negative there? Well, think about it. This modeling how the height changes per time, right? So if the height is changing in a negative way per time, think about what that means. It means that the ball's height is decreasing with time. So the ball is basically falling back down between 2 and 4 seconds. Lastly, we're asked to find the rate of change in the 3rd second and in the 4th second. Now, what does that mean? This sort of sounds like an instantaneous rate of change, doesn't it? But it's really not. When you think about what the 3rd second is, right? The 3rd second means, well, actually, let's go back. Let's think about what the 1st second would mean. The 1st second would be between 0 and 1, right? The 2nd second would be between 1 and 2. So the 3rd second, would be between 2 and 3 seconds, right? So basically what we need to do is we need to find the height at 2 seconds, the height at 3 seconds, and find our average rate of change. I'm going to leave that up to you, and then do the same thing for the 4th second. I'm going to leave that part up to you, so pause the video now, and I will just put the answers here, or the solutions here for you to see in a second. Okay, so here's our answer as it says at the top of the page, right here actually. First I calculated what h at 2, 3, and 4 were, because you need all those to calculate these. And then I calculated at the 3rd second, it was negative 5 meters per second, so again it's falling. And in the 4th second, between 3 and 4 seconds basically, and that's also falling at a rate of negative 15 meters per second. So it's basically speeding up in the negative direction. Lastly, we have a bit of a thinking problem here. Determine the value of A is what we're determining, so that the average rate of change for that function, j of x, has an average rate of change of 8, basically, between negative 1 and 2. So that's going to be some quadratic, and we got to find out the a value that makes that true. So I want you to pause this. I want you to try this one yourself. Think about what we have and what we can use to try to solve this problem. So if you're stuck, I've started it a little bit for you. I just took our average rate of change formula, our y2 minus y1 over x2 minus x1, and I've plugged in what we do know. So j at 2 minus j at negative 1 over the difference in the x values, 2 minus 1. Actually, that should be 2 minus negative 1, right? So again, pause it here and see if you can figure out what to do from here. So again, another hint if you're stuck. Look what I've done. I've plugged in j at 2. So basically, you replace x with 2 in your function, and that's what this first part is right here. And then I did the same thing for j at negative 1. Notice how both of these have an a in them. I also simplified the bottom to make it 3, and the average rate of change has to equal 8 as per the question. So now it just becomes an algebra problem you should be able to solve for a. So go for it. So there we go. There's the algebra. When you solve for a, you should get an answer of 5, as it says the answer should be there.